Good evening and welcome. Thank you for joining us to celebrate the appointments of Dr. Sudha Chakrapani as the Joseph T. Warren, MD, University Professor of Medicine, and Dr. Sam Messiano as the William H. Weir, MD, Professor of Reproductive Biology. It is my honor to chair the session this afternoon evening. I'm Stan Gerson, Interim Dean for the School of Medicine. First, I'd like to welcome Dr. Chakrapani's family and Dr. Messiano's family who are joining us on our webcast. Dr. Chakrapani's parents, Gopal and Vida Chakrapani, her husband, Pradeep Pinto, and their children, Sophia and Rohan. And to Dr. Messiano's wife, Laura, children, Luke and Sarah. And I'd like to make note of Dr. Messiano's siblings, in-laws, former members of his laboratory who are joining us this afternoon as well. First, I get to remind you about just how important and significant in the academic world a endowed professorship induction is. We really do honor our best and brightest faculty, some of them more senior, some of them more junior. Thank them for the contributions they make and will continue to make in our community of educators and investigators, and the ultimate benefits that those efforts, both in investigation, treatment, and discovery, will bring to human health. We know that developing an academic career, pursuing an academic career, keeping your mission to help our fellow humans is a fiercely competitive one for top talent, and that we need to boost our best faculty in any way that we can. And our named professorships, our endowed professorships, are our way of noticing the remarkable achievements of our best faculty. And we want our faculty to add those named professorships to their byline, to their writings, to their correspondence. Keep it in mind. And for those of us who have an endowed professorship, there's nothing more enjoyable than to add that endowed professorship at the end of one's name. Currently, the School of Medicine has more than 120 endowed professorships. We've added about 4 this year. About 2/3 of those came in the past decade during the university's forward-thinking campaign over the past eight or 9 years in particular. Some of our chairs are quite long-standing, such as those 2 this evening, and some are just having their first installation. And we are incredibly grateful to the donors, the community of donors, and their offspring who have made these professorships possible. And whenever we can, we keep in touch with the offspring of our more senior professorships. Now, the Warren Professorship, if I could start with that, is named after Joseph Warren, a hallowed name for the university and for university hospitals. He received his BA from Davidson College back in 1913, and his medical degree from Harvard Medical School in 1917. I'll remind you that he was an intern during the 19 pandemic. He served his residency in Boston, then as an instructor at the University of Pennsylvania before joining the faculty of Harvard Medical School. And he came to our school in 1929 to serve as the dean of the school, and then served as the dean of the School of Medicine between 1945 and 1959. He was an officer in the medical corps of the U.S. Army briefly in World War I. He published articles on kidney and heart physiology. He was really in that first generation of physiologists, and much of what we know now worldwide is in appreciation of his early studies in kidney function and disease. I should also note that during World War II, he was a medical consultant to the Secretary of War, I guess just before he became the dean, and was awarded the Medal of Freedom. As dean, he enlarged the faculty, strengthened the financial position of the school, but most importantly, in 1952, he took on an effort to revolutionize medical school curriculum at Case Western, teaching medicine as a whole concept rather than a series of unrelated disciplines, teaching subject areas by committees of faculty members rather than by departments. Began the block concept, which carried medicine across the country for the next 4 decades. In fact, we still have his vision statement. I actually have a recording of that, which I'll share with Sudha, about the curriculum, in which he clearly states that he would have as many meetings as it took with the faculty to make sure that they understood and appreciated his concept for a new curriculum. Maybe all deans should keep that in mind. He was the first recipient of the University Medal for Outstanding Service in 1973. And it was really a collection of his friends and colleagues who put together the resources that became one of our most esteemed professorships that we have. I'd like to move on to the Weir Professorship, which is also a legacy professorship. Dr. William H. Weir, equally accomplished, established a flourishing gynecological service at university hospitals in the early 1990s. In the early 1900s, at a time when Lakeside Hospital was just in the process of moving to its current location. He was passionate about allowing women to take an active role in family planning and dedicated his career to promoting and protecting women's reproductive health. He was a member of the first medical advisory board of the Independent Maternal Health Association, which was established in 1928, which provided at that time the available birth control to married women. It had been previously an illicit service, unavailable at most facilities and hospitals, and therefore he set this up independent of Lakeside Hospital. It was the first of its clinic of its kind in the city of Cleveland, one of the first of more than 50. It later became part of Planned Parenthood of Greater Cleveland. In 1936, Dr. Weir served as the director of the gynecologic service for the newly integrated obstetrics and gynecology department at McDonald House. Dr. Weir served as its director from 1936 to 1950. And his family and Dr. Weir used their assets to create a fund more than 50 years ago in reproductive biology research, and over time, that was able to be converted into the current William H. Weir, MD, endowed professorship in reproductive biology. So with that history lesson, I'd like now to move on and introduce Dr. Walter Boron, and later I'll introduce Dr. James Liu, both of whom will introduce sequentially the recipients of these prize professorships. Dr. Boron holds the David N. and Inez Myers Antonio Scarpa Professorship and is chair of the Department of Physiology and Biophysics. He was named a university distinguished professor in 2020. Now, Dr. Boron studied his medicine and physiology at the University of Washington, St. Louis. After completing his MD and PhD, he joined Yale as a postdoctoral fellow, joined the Department of Physiology, and served as a stint as the chair of that department before being recruited to Case Western School of Medicine. His current research focuses on intracellular pH homeostasis, an absolutely fundamental process of all living organisms and all efforts of cells. They require a pH and they require a static pH, whether it be cell division, metabolism, channels that cells use to communicate, transporters, structural proteins, and the like. If you don't have the proper pH, the cell just won't survive. And across the world, Dr. Boron is recognized as one of the few people who both understands it and can explain it. I hope he's not going to give us a lecture this evening, but we'd learn a lot if he did. Among his national recognitions, he was the 72nd president of the American Physiological Society. He's currently Secretary General of the International Union of Physiological Sciences. He was inducted into the National Academy of Medicine in 2014, received the Homer Smith Award from the American Society of Nephrology in 2005. So you might wonder why it took the university so long to recognize him as a distinguished university professor. Walter, it's my pleasure to have you introduce Dr. Chakrapani.
Thank you so much for the very kind words about me. But of course, this is not about me, but about our inductees. And I'm deeply honored and indeed delighted to introduce Professor Sudha Chakrapani. So as by way of background, Sudha obtained her PhD degree in 2004 at the University of Buffalo under the advising and mentorship of Tony Auerbach. Later on, she did her postdoctoral fellowship first at the University of Chicago, Virginia, and then at Chicago with Eduardo Perozzo. She was a research assistant professor, then continuing on at the University of Chicago until we were fortunate enough to recruit here to Case Western Reserve University, first as an assistant professor in 2010. She rose through the ranks and became professor in 2020 in the Department of Physiology and Biophysics. Sudha's research is in the area of studying the function of ion channels. And in particular, she's interested in studying pentameric ligand-gated ion channels. So ion channels are important in cells throughout the body because they're the mechanism, the conduit by which ions can move into or out of cells. And so in the brain, we all know that these are important for action potentials, but in the heart, similarly important for action potentials, and muscle for action potentials. But in cells throughout the body, these are important for signaling and maintaining the membrane potential of the cell. Stan was saying how important pH is, but the membrane potential of cells is also extremely important because so many membrane proteins are voltage sensitive. In particular, she's interested in pentameric ligand-gated ion channels, such as the serotonin receptor, excuse me, and these channels, when they bind a signaling molecule floating around in the extracellular fluid, then open up, they're called pentameric because there's 5 subunits that surround the pore through which the ions move. Sudha is especially gifted because she's a multidisciplinary scientist. Rather than focusing on one particular technology, she focuses on solving a problem with a very diverse and complementary toolkit. One of the members of the toolkit package is patch clamping. This is a very elegant mechanism approach in which one can watch the electrical currents flowing through even a single ion channel. Also, as a technique, I'll tell you just much more about it later, called EPR, which allows one to watch how the channels take on different shapes in real time. X-ray crystallography allows one to obtain high-resolution structures at the atomic level of these channels that she's interested in, and cryo-electron microscopy, high-resolution structures of channels as well, is the most recent and most powerful version of these techniques for obtaining the structure of membrane proteins. And so Sudha's approach for using at least these 4 and even more kinds of technologies that I'm not going to tell you about this afternoon have been extremely important in being able to look at the function of these ion channels from many different perspectives. And the goal of a scientist is to change the way that people think. And she's done a wonderful job teaching us how to think differently about these channels by obtaining full-length structures of these channels, by obtaining the structures of the channels in different conformations. So this channel just doesn't sit here like this. The channel has to be able to open up to allow the ions to go through, but then close back down again. And as the channel goes through these changes in the structure, those are called conformations. She's been able to obtain the structures of some of these channels in different conformations, and that's been an extremely powerful advance. She's also been able to obtain the structure of these channels and study the channels by these various technologies that I've described, looking at drug receptor interactions. And she's published her research in very prestigious journals. In particular, I'd like to point out 3 papers that she's had in the journal Nature. And in 2018, most recently, she published a paper that demonstrated 2 distinct structures, serotonin-bound structures of the serotonin receptor. It's not just a receptor, it's also this pentameric ion channel. The impact of Sudha's work on the community, she's been a wonderful service member of science, not only locally, but nationwide. At the level of the National Institutes of Health, she's been a permanent member of the BBM study section, biophysics of membrane, and she's responsible for reviewing grant applications. At the Biophysical Society, she plays multiple roles. One of them is she's their representative and therefore the associate editor of a very prestigious journal called the Biophysical Journal. At Case Western Reserve University, Sudha is had been chair of the Faculty Council, which is an extremely important role here at the School of Medicine. Also at Case Western Reserve, she's recently been appointed director of the Cleveland Center for Membrane and Structural Biology. And one of the components of that is that she's also the director of the cryo-electron microscopy core, which has a high resolution Titan Krios EM, which is capable of obtaining these structures at very high resolution of various proteins, including membrane proteins. Another area where she's been important in service here at Case Western Reserve University is she spearheaded an equipment grant. These are known as S10 grants that allowed the purchase of a very expensive piece of equipment called a pulsed EPR. That's an electronic paramagnetic resonance magnet and electronics that go along with it. And that's used by her and a number of other people here at the School of Medicine and around the university. She also, as the head of the director of the Cleveland Center for Membrane and Structural Biology, has spearheaded new educational initiatives, including a new T32. This is a training grant in education that has been recently submitted by her. In addition to all of the honors that are implied by the introduction I provided so far, Sudha has recently been awarded a R35 grant from the NIH. This is called a MIRA grant, and this grant is highly, highly competitive and combines several projects into one large project and allows the researcher to work for several years unimpeded on an important research project. And in Sudha's case, of course, this is understanding the function of these pentameric ligand-gated channels. And most recently, of course, Sudha has been awarded the Weir Professorship. And before I leave the introduction, I'd like to say that Sudha is a multidimensional lady. In addition to all of her science that she's doing, she enjoys diversionary endeavors such as reading and traveling and cooking. And although she's a vegetarian, she has a particular expertise, I understand, in cooking meat dishes. And I think her expertise was recently challenged by Witold Sorevich in our department, who challenged her to cook something with meat in it. And Sudha surprised him with an outstanding dish of curry with meat in it, and Witold was impressed, and I think that this demonstrates the well-rounded nature of our most recent Weir professor. So without further ado, I'd like to introduce Sudha Chakrapani, our new Joseph T. Weir, MD, University Professor in Medicine. Sudha.
Thank you so much, Walter, for the very kind introduction and for the funny note at the end as well. Let me share the screen here. Right. And this is truly an incredible honor, and I'm very, very grateful to the Weir family for this professorship, which has really supported our research initiatives and our plans ahead. So I'm told that I need to give a summary of my life's journey, both my professional and personal path in 10 minutes. So here is my attempt at capturing some of the high notes. So let me start off with something from the very beginning. I was born in India, in Madras, or now called Chennai, in the south of the country. My dad was an officer in Indian Air Force, and that meant traveling across the country. We moved every 3-4 years. We were in different schools, different places, with new friends each time. Thought it was a lot of fun, but I think along the way, we were also learning to be more adaptable and being resilient. So I think it has served me well to this date. So here is a Bollywood style picture of my family. We've had a very humble beginning, and my parents were really motivated and passionate about education. So they essentially gave everything they had to raising three ambitious daughters, and all of us were driven towards profession in science. Nirupama has a PhD in material science from Rensselaer Polytechnic Institute. She directs her team, technology development team at Intel Corporations. Vidya has a PhD in chemical engineering, actually from Case Western. She's now a professor at Rensselaer Polytechnic. So I think my parents really are the center of all of these efforts, and they continue to support us to this day. So before I tell you about my career path to here, a little bit of introduction. Walter had done a superb job of laying the foundation for this. So we are interested in understanding the electrical communication between brain and different parts, different organs of the body. And we're particularly focused on this junction between a nerve cell and another nerve cell, or a nerve cell and an organ system. And this specialized region is called a synapse. And we are focused on these type of proteins called ion channels that we see are as transducers of signal, being chemical to an electrical signal, or starting from an electrical signal to another electrical signal. By way of this, ion channels are central to many of the functions that define life. For example, movement, breathing, gut functions, learning and memory, or even pain perception. So what happens when things go wrong with ion channels, when there is a mutation? It leads to many kinds of disorders and diseases: epilepsy, psychiatric disorders, chronic pain, which has been really hard to treat, muscular dystrophy, and even drug addiction. So naturally, ion channels are targets to many therapeutic compounds, from anesthetics to antidepressants to antiemetic or anti-vomiting agents. So what do we want to do? So we want to really understand how these channels work. How do they sense stimuli, and what happens when there is a disease-causing mutation? How is it altering its function? And how do drugs are able to do what they do? Like, how do they bind, and how do they correct the dysfunction that we are seeing? So my earliest introduction to bioelectricity was when I was a master's student in biomedical engineering at Indian Institute of Technology. So I was working with Professor Rohit Manchanda. We were looking things at a more system level. We were screening for natural compounds and their derivatives for their effect on muscle contractions. We were looking at frog, sartorius muscle. And we were studying how these compounds inhibit muscle contraction, and these drugs had potential to be used as muscle relaxants. Interestingly, we were studying blockers of acetylcholine receptor, a type of channel that I continue to work on. So Rohit was trained in Oxford, and I really enjoyed his lab culture and his approach to science. That these interactions really cemented my resolve to study abroad. So in '99, I came to University at Buffalo to pursue my PhD. So I met my advisor, Tony Orbach, in a meet and greet event where these graduate students get to interact with the professors. So Tony was talking about acetylcholine receptors, which I was familiar with, but he talked about how you can study these at a single molecule level. And I was quite awed at how this can be done. So he asked me to spend some time one afternoon, come by the lab and look at how patch clamping is done. So it is a method that Walter mentioned. Is you capture a part of the membrane and you look at one or two or few ion channels and their electrical behavior. So this is this sort of a recording where you can look at channels going open right here, closed right here. You can see these fluctuations. And what Tony told me that day was, when you watch ion channel behavior in real time from one single molecule, you're really going to be hooked onto ion channels for life. And that actually happened to be true. And so we, over the next 4+ years, I studied over hundreds of mutations in acetylcholine receptors, looking at how these mutations modify the functional behavior of the channel and what it tells us about the overall function. Tony was very passionate about science. He was always there in the lab, and I could reach out to him anytime during the week or weekend to tell about an interesting idea or an intriguing result. He was always there. And that sort of showed me what you can be when you have your own independent position where you can just follow science where it takes you. So I really knew that academic life was what I wanted. And so I went on to pursue my postdoctoral work with Eduardo Perozo. At that time, he was in the University of Virginia, and then I moved with the lab to University of Chicago a couple of years later. So I met Eduardo at a Biophysical Society meeting. He was giving a new and notable talk. His group had just uncovered how a mechanosensitive channel responds to changes in membrane tension. And so he showed how he was using EPR spectroscopy to look at protein movements, and he was looking at functional analysis at the same context of membrane tension. And I was just fascinated by how a multidisciplinary approach can actually, it's so innovative that it can answer some fundamental questions which are really difficult to address with a single technique. So I joined his lab, and in the years that I spent there, I studied several different voltage-gated potassium channels and sodium channels by electrophysiology, by X-ray crystallography, EPR, and we collaborated for molecular dynamic simulation work. So I really enjoyed Eduardo's mentorship. He treated us like colleagues, and we had the freedom to explore, to be creative, and just pick up on new technologies. So I think that all of that independence came with the responsibility that you really needed to own your project. And I think I'm very grateful for those experiences. And I think I tried to sort of emulate some of these here in the lab as well. So I came to CASE in 2010. So this is this lovely brand new space that I had. So I was super thrilled, and I guess this is a picture of an excited, nervous PI just setting up the lab, and I can't believe it's 10 years already. This past 10 years has been a blast. So we went on from looking at things in a very minimalistic way to really growing our science. So all of the approaches that I mentioned earlier require you to work with a simpler version of the ion channels. The human channels are extremely complex, and they are extremely in a very complex environment. So we were lucky that when we were starting out the lab, several homologs of acetylcholine receptor family of channels were discovered in bacteria. So we started with these. It was very fascinating because these channels look very similar to acetylcholine receptor. They function similarly. They even have drug sensitivity in the same range as the acetylcholine receptor family. So we did a lot of work looking at them by X-ray crystallography, by EPR. We found how these channels respond to stimuli, how they are modified by lipids that are exclusively that are enriched in synaptic membranes. So when we were working with these, somewhere in 2014, cryo-EM or cryo-electron microscopy became a technique that revolutionized structural biology. This is an imaging approach that was really suitable for large macromolecules and viruses. But because of the technological breakthroughs, it started to become amenable to smaller proteins that like the ones we're working with. So we were fortunate to find a collaborator here, Weir Bell, who was trained in cryo-EM. We collaborated. She facilitated the training in our lab for cryo-EM. We were supported by NIH Technology Transfer Funds and several national workshops that enabled the lab to get on board with this. And we were successful in solving the first full-length structures of serotonin receptors. We eventually showed where does serotonin bind, how it activates the channel, and we also found the binding site for drugs that are used in the clinics for patients that are undergoing chemotherapy and radiation therapy. They have intense nausea and vomiting. So the drugs called citrons, which alleviate these effects, bind to these receptors. So again, we are looking at other drug binding pockets. We're looking at how you modify these drugs to have better efficacy drugs. And then we went on to more complex receptors also. So this is from glycine receptors. We're able to achieve similar findings or similar level of understanding. We've also looking at these receptors in a membrane environment and trying to see how these influence function. Where are we headed from here? Well, the synapse, as we know it, is extremely complex and really very crowded. So I showed you a simple version of synapse with one channel, but a synapse, the ion channels in the synapse seldom work alone. They are in an interaction network with several interacting partners. So this is even a very simplified version of synapse. And so an analogy is we are looking at a very crowded place. What we are doing right now is zooming in on this one particular channel to understand it. This is even simpler. We are not really looking at zooming in on one in its native context. We are actually looking at it in isolation. So what we have to do is go backwards to creating these interactomes and eventually looking at the synapse in its entirety. So that's the holy grail, and that's where we would want to be, and that's a level of knowledge we want to achieve. Let me sort of wind this up by acknowledging the people who have made this possible. And I must tell you that I am where I am because of my trainees and my group. I've been extremely fortunate and privileged to work with this extremely talented group of people. They bring in such diversity in thinking. They come from very diverse backgrounds, and they have enriched our science in many different ways. I really enjoy seeing their perspective. Same problem, but how do they look at it is so different. This is my group of people who have graduated or finished their postdoc from the lab. They're all in science and have done very well, both in academic setting as well as in the industry. So guys, this celebration is celebrating you. And my collaborators, we've had very diverse group of collaborators as well, from cellular to molecular dynamic work to cryo-EM studies. They have really provided new perspective to our research, new directions, new flavors to what we do. So a big shout out to their contributions. And finally, I want to thank Walter Boron, my chair, who recruited me. He trusted in me. He believed in me. I'm very grateful for that, and for a very collegial environment within our department. My mentoring committee, Vito Surevitz, Steve Jones, and Corey Smith, and physiology faculty and staff. This has been a great experience in the last 10, 11 years, and I'm grateful for that. I also want to say a big thank you and acknowledge the efforts from our former Dean, Pam Davis, who laid the foundation and paved the way for high-resolution cryo-EM infrastructure here at CASE. And I want to thank our current Dean, Stan Gerson, for his tremendous support to grow the structural biology community here at CASE Western. And finally, this is my family. I want to acknowledge right here my husband, Pradeep. I met him in grad school. He's been there throughout this ride, and he's really supported me through this whole process. And it has taken many sacrifices. So he comes from a very different background in science. So he is an aerospace engineer. He works at Eaton Aerospace. He has a demanding career, but he's really found ways to be there and support me. And that has included 3 hours of daily commute so that I could stay close to my postdoc lab, and switching jobs and moving with me when I had to move institutions. So really, and countless daily efforts that has taken in so that we can grow together both professionally and personally. And our lovely kids, Sophia and Rohan, the joy of our life, they complete us, and they essentially make everything, all our struggles and everything we do worthwhile. Love you guys. So this is it from me, and thank you all for joining, and it's really an honor, and thanks for being there.
Thank you very much, Dr. Chakrapani, for a wonderful and incredibly well explained topic, which most of us don't think about, single molecules every day and how they function and work. So I appreciate that, and I'm sure all of us did. So thank you very much. I'd now like to introduce Dr. James Liu, so that he may introduce our next recipient, Dr. Messiano. So let me tell you just a little bit about Dr. Liu. He is the chair and professor of the Department of Reproductive Biology in the School of Medicine and at university hospitals. He's board certified in obstetrics and gynecology with a subspecialty certification in reproductive endocrinology and infertility. He graduated from the Ohio State University School of Medicine and then trained in OBGYN residency at the University of Rochester Strong Memorial Hospital, not too far away from Buffalo. He completed a fellowship in reproductive endocrinology at the University of California, San Diego, where he then became a professor certification in reproductive endocrinology and infertility. Maybe I can add to it. Thank you. And then he was appointed assistant director in that department and director of the department's radioimmunoassay core laboratory. He was appointed the chief of the head of the division of reproductive biology and endocrinology and infertility and professor in OBGYN at the University of Cincinnati. And then in 2001 joined UH McDonald Women's Hospital as chair of the Department of Obstetrics and Gynecology, a position he currently holds. Dr. Liu is listed as in the Best Doctors of America as a consultant for the FDA and several pharmaceutical companies in the area of reproductive biology and infertility. And his own research interests are currently focused on what causes the fertilized egg implantation event to fail. And findings of his research have suggested that uterine blood flow is a major factor in this process. So with that background and knowledge, he's the perfect individual to introduce our chair recipient this evening, Dr. Sam Messiano. Dr. Liu.
I apologize for being a little bit late. Was seeing a last patient with oncofertility issues. So I do apologize for being a little bit late. But it is my pleasure to introduce Dr. Sam Messiano, who we recruited as a PhD scientist from the University of California, San Francisco. Sam, as you'll hear him speak, is a native Aussie. He did his research PhD in Australia, but did postdoc with one of the premier reproductive endocrinologists, Dr. Jaffe at UCSF, the late Dr. Jaffe, in the area of adrenal physiology and fetal adrenal. And in Australia, lots and lots of sheep. So he is very familiar with sheep models. And one of the best models probably for placental physiology and the area that he had focused on after his adrenal physiology was the aegis of what causes labor. And unlike the human model, the sheep is somewhat different than the human. Sheep placentas are different than human placentas. And in sheep, the control of the parturition or the birth, the timing of birth is very different from the human. And so Sam began to focus on the role of progesterone in maintaining pregnancy and what happens to progesterone in labor to cause labor to be triggered spontaneously in the human. To that end, he has started with obviously an animal model, but progressed rapidly to saying it's not the model that we really need to study. We need to study human model. And in that sense, he has pioneered some of the techniques in studying human myometrium. So we saw Sam, once we recruited him, going down to elective C-sections at all hours of the day and night and collecting myometrial cells from C-section patients and isolating them. Over the course, he found that there were differences in the performance of the two types of progesterone receptors in the human myometrium, and there were differences in the concentrations of these two receptors. And he developed a hypothesis that the progesterone receptor A and progesterone receptor B were different in their performance, with B being the predominant one being responsible for quiescence of the uterus, and A being one that perhaps counteracted that role. And the ratio of these two may play a tremendous difference in why labor occurs, even though the progesterone levels in the human do not really fall at the time of parturition. This is very important because preterm labor is the primary cause of increases in fetal mortality, especially in women that we see in the Cleveland area. And premature deliveries is responsible for a significant number of fetal deaths and fetal morbidity and mortality. So Sam set about to study this, and he has pioneered some techniques in which he's engineered progesterone receptors to be in cell lines so that he has the ability to turn on progesterone receptors and turn off progesterone receptors at will, engineering the receptor to be turned on and turned off with antibiotics as the trigger. And so he's able to study those. He has been successful at getting funding from NICHD. Sequentially, R01s, as well as Gates Foundation funding to look at various types of progesterone analogs to see which ones could be developed perhaps for treatment of and prevention of preterm labor. Additionally, Sam is the lead investigator for a multi-center March of Dimes grant awarded to CASE in collaboration with Ohio State and the University of Cincinnati, with our goal of studying the progesterone receptor and studying progesterone analogs in the prevention of preterm labor in collaboration with some of the investigators at Metro as well. So Sam has been continuously funded since he has been in our institution. He has taken over from Neil Rote as the director of our research in the Division of Research in the Department of Obstetrics and Gynecology, as well as reproductive biology. Sam right now is responsible for running the core labs on the 8th floor of McDonald Women's Hospital. He also is mentoring some of our MD postdocs in both the Maternal Fetal Medicine Fellowship Program, as well as the reproductive biology, reproductive endocrinology program for our fellows. So Sam has really distinguished himself as a really key mentor, along with Dr. Rachel Wienerman from our on the MD side. And he has assisted in starting a mouse IVF laboratory with Dr. Wienerman. And so we have a unique tool set to begin to explore some of the changes in the human model in terms of IVF and how IVF performs with our various pharmacologic manipulations that we do on a routine basis. And I think Sam is totally deserving of being selected as the Weir Professorship. So let me close there.
Thank you, Jim. Now we'd like to hear from Sam.
Thank you, Jim, and thank you, Dean Gerson. First of all, this is truly an honor, and I feel somewhat overwhelmed in many respects because I'm just a simple meat worker from a long way away. As Jim mentioned, I did my PhD using sheep as a model. And in the sheep lab, we used to call ourselves meat workers. And in fact, that's what effectively we were. And I still go back to those roots whenever I find myself wondering what the hell is going on in the lab, and think, how the hell did I get here from there? But in any event, I really want to thank, first of all, the Weir family for their generosity in establishing this endowment. William H. Weir, as Dean Gerson mentioned, was a pioneer in not only establishing the OBGYN department at UH, but in women's health and women's reproductive autonomy. And the work he did in the 1920s, I'm sure, when contraception was very, rudimentary, was fundamental to stuff that came after that. And so I'm very appreciative of the Weir family for establishing the endowment, and feel humbled to carry on that endowment. To Dean Gerson for producing an environment at Case which I can really call my academic home, and to previous Dean Pam. It really is, my kids ask me, what do you do? And I said, I don't know what I do, but it beats working for a living, because every day at work is just a joy in many respects. And we're just tinkering, doing research. And so the environment at Case is just outstanding, and being around people who have the same level of curiosity about science and about health in general, and I feel privileged to be in that environment. And to Dr. Liu, who recruited me in 2002, I bumped into a previous member of the research division at UH at a meeting, and we literally bumped into each other. And it was in San Diego, and I said hello. He said hello, and I said, where are you from? He said, Cleveland. I said, I have family in Cleveland because my wife has roots in Cleveland. And he mentioned Dr. Liu. I sent Dr. Liu a letter, and within 2 years, I was settling the family in Shaker Heights. So it was a chance event, but Jim saw the potential in me, and I'm grateful for that. And so we can move forward. There's other people I really do need to thank before I talk about what I do and how I got here. Neil Rote, as Jim mentioned, was the professor who held the Weir chair before I became before now, and Neil was the senior person in the research division to whom I saw as a mentor. And Neil his office was down the hall, and as I was writing grants, I would run them past Neil, and he would always say, "You sure you want to do it that way?" And he got me thinking. He got me arguing with him. Sometimes I won and sometimes he won, but that's what it's all about. And in the end, we produced a much better product in research because of this interaction I had with Neil. And all through the 10 years or 12 years that we were collaborators, it was a ton of fun just sticking my head in his office and hearing his rants about his kids and everything you want to point to under the sun. Neil left. I had the opportunity to work with Charles Malmed, who also became a mentor in many respects. He read my grants and critiqued them, and that was just amazing to me, the feedback he gave me, and he made my science better. So thank you to Charles. On the list here, I've got Greg Crop, and there's a lot more people than this, but these people I really need to thank. Greg and Focko, we have an R01 essentially together to develop selective progesterone receptor modulators as therapies to prevent preterm birth, and I'll talk about that in a minute. But it's just a hoot having meetings with Greg and Focko. I always leave smarter than when I come in, and again, they're able to focus my thinking and provide technologies that I would never have thought I could be associated with. Greg looks after the synthesis of the organic compounds that we use, and Focko does the in silico modeling of the progesterone analogs in the ligand binding pocket of the progesterone receptor. Other people are John Moore and Mehmet Koyatürk and Wendy Goodman. John has, I've collaborated with John on several grants now looking at the maternal fetal interface and how progesterone is acting to keep the membranes, the bag that the baby is enclosed in, keep it strong, and why it weakens at the end and you get rupture of the membranes. Mehmet Koyatürk is an outstanding systems biologist, and we do a lot of big data work, and I would be completely lost if it wasn't for Mehmet, who he and his graduate students will take our data sets and actually put meaning to the biology that we're trying to decipher from these massive data sets. And recently, Wendy Goodman, who is an outstanding immunologist, and we've started a collaboration in conjunction with the March of Dimes Ohio Collaborative. And Wendy is really teaching me immunology. I'm not an immunologist, but there's something going on with the immune system that allows a woman to be pregnant. When you think about it, the baby is a foreign entity in the pregnancy, and the maternal immune system should theoretically reject those cells, but it doesn't. And so we're trying to understand why it doesn't, and whether or not defects in that pathway are responsible for some cases of preterm birth. And then on the clinical side, David Hackney and Rachel Wienerman. So Dave is the MFM division director at UH, and everything I do with human tissues, I owe to Dave Hackney, who is the sounding board for what's happening with the boots on the ground in the clinic. And so our conversations, he usually brings, when I have these crazy ideas about the way things might be working, he gives me a clinical perspective about what actually happens at the coalface when he treats a patient. And Rachel Wienerman, who's recently joined us, or recently, last 5 years. So Rachel and I co-mentor the reproductive endocrinology and infertility fellows who work up on the 8th floor in the research division, and we have a lot of fun establishing the mouse embryo models and mentoring the REI fellows. So these are just a few of the people that are part of my academic world at CASE and have helped me to further my research, which really isn't my research, it's our research. And I also want to thank the clinical faculty at STAR and staff in the OB/GYN department that really is a reflection of Jim Liu. I'm always amazed at the compassion, the professionalism, and just the all-round, the good nature of the staff who really put women first. Their patients are first, and I'm inspired by that. And the MFM and REI fellows that are part of that whole process, the trainees who come through the lab, I'm constantly learning from them about what happens in the clinic. I really do need to thank Walter and the Department of Physiology and Biophysics faculty. I'm a secondary appointment in that department, and it always is a go-to for me when I don't understand something that is physiologic in nature, and I can always find somebody in the physiology department who's willing to collaborate or be a co-investigator on a grant or provide me with some advice on techniques. So that has been a major asset for my development as a scientist. And it's not just science we do. I really enjoy the other academic aspects of being in a university environment. And the School of Medicine teaching side of the equation is something I get a lot of joy out of, and it's the faculty, Amy DeFos, and all the others that are involved with Block 2 of the medical school curriculum. It's just a hoot to not only teach the students, but to be part of developing the curriculum and seeing how these just incredible young people during their journey through medical schools, to see how they mature. All right, so research isn't done by me, it's done by the people, the team in the lab. And so I just want to acknowledge some of those people. There's been a lot. Jim had the foresight when I first got here to, the research division was essentially decimated. Everybody left when the previous chair left. And so there was nobody up there. But Jim had the foresight to keep the technical, the research assistants and the research associates in place. And I really owe everything in the work we did in the last 15 years. Weijing Tan and Li Juan Yi, this is Li Juan here and Weijing there, husband and wife team that have been in the research division at OBGYN and reproductive biology department since the late 70s. And they knew where the skeletons were buried, and anything I needed, they were able to figure out. And both of them knew little about cell biology and molecular biology, but they soon came up to speed, and I could rely on them to just take a project and go for it. Tony Walsh and Amy Molino were trainees in the lab. Tony was my PhD student in Newcastle in Australia, and then came over to do a postdoc, and we had a lot of fun together moving the ball forward on understanding how estrogen signals in the pregnancy uterus. And Amy Molino was an MFM fellow who was at Metro at the time, but did some brilliant work when she came over to do her research project in the lab. So that was version 1.0, and then as funding increased and decreased, the lab grew and the lab shrunk. People left to do other things, and so a lot of these people here, you can see that Weijing and Li Juan stayed. They've been a centerpiece of the lab. Greg, Yelena, Junyi were all instrumental in developing model systems and moving things forward. Rachel, Wissam. Interesting story about Wissam that I could tell, I could go on. Just wonderful people. Pavand did some beautiful work on the phosphorylated forms of the progesterone receptor. And Doug Brubaker at the back here was a systems biologist who just took our work to the next level. He was a graduate student with Mehmet Koyturk and Mark Chance, and it was amazing the work that he did to help us understand how progesterone is signaling in the uterus. Messiano Lab 3.0 was a bunch of young people that we had a ball together. So we had fun and we did good science at the same time, which I think is the recipe for really moving the ball forward. Rachel, Callista, Jessica, and Carlos, all of them have gone on to bigger and better things, medical school, law school, and this is the problem you have when you hire people in their 20s. They're all moving towards something else. And Zach Stanfield was a PhD student, again, in systems biology, so he was able to take a lot of our big data sets and turn it into something we understand. And Angela Di Tommaso, who is the current PhD student in the lab. Here's Angela right here. She's the boss right now. She has all the corporate memory. And now we're in version 4.0 with Sarah, Soma, and Peter, who started in the lab just a couple of weeks ago. So we're in the process of learning techniques and coming acquainted with the questions we're asking. So it's a lot of fun going through the process and reorganizing everything. And then in the image here, you've got two of the outstanding REI fellows, Raya and Rebecca, who are working in the lab right now. So I really do, there's a lot of OBGYN residents and fellows who have cycled through the lab that I really should acknowledge, but there's no room to list them all. Medical students come in and out, and it's just a hoot having them in the lab. And undergraduate students as well will spend some time doing projects in the lab. And so I really owe everything we do at the bench to these people. So what do we do? So what we're trying to understand is how is the timing of human birth controlled? So the process of parturition, labor and delivery. So what determines when birth happens? And what we study is the uterus, and it's a remarkable organ, the uterus. It's essentially a bag of muscle, or a bag made up of muscle that has a gateway at the end, the cervix, and an inside lining called the endometrium or decidua that is conducive to implantation. So this is the area where the embryo loves to implant. Okay, it establishes a pregnancy, and that pregnancy develops. The fetus grows, the placenta grows, and everything is great. The uterus grows to a certain extent. It stretches to accommodate the growing fetus. And for 40 weeks, this bag of muscle is kept in a relaxed and quiescent state. Okay. And so suddenly something happens to cause the muscle of the uterus to contract, and not only contract, but on a per weight basis, it becomes one of the most strongest muscles in the human body. So it's stronger than the glutes. And so that's remarkable to me, that this muscle that is supposed to contract in order to empty the contents of the uterus for 40 weeks does not contract. Okay. But at the initiation of parturition, the muscle begins to contract, the cervix actually dissolves and dilates, so the gateway opens. And when the muscle contracts and the gateway opens, there's only one place for this fella to go, and that is out. And so that's essentially how birth happens. And the membranes, the bag that is containing the fetus, begin to weaken, and they rupture with the contractions. Sometimes they rupture before the contractions start, but that weakening is critical for the process of labor and delivery. So we wouldn't be here if it wasn't for this bag of muscle. Okay. And so, as I said, we think about the process of labor and delivery as the muscle contracting, the contractions of labor starting, the cervix dilating, and the uterus emptying. But what's really amazing to me is that, so what? This is a bag of muscle. That's what it's built to do. It's built to contract and empty. Why is it not doing that for 40 weeks? And so when we thought about that, we thought, well, that's really interesting, but it's not always 40 weeks. And the problem here, the major clinical problem that we're addressing is the issue of preterm birth. So if you look at the graph here, this is the percent of births per gestational week, okay? So most 80% of all births happen between the 37th and 42nd week of pregnancy, okay? And that's really fine. These babies are born healthy and everything's good. But 15% of all pregnancies deliver before 37 weeks. And the earlier that you deliver before 37 weeks, the more chance that neonate will have a really hard time staying alive and breathing air and doing everything it needs to do to live outside of the uterus. And so preterm birth is a major problem. It affects 15% of pregnancies worldwide. It affects around 15 million babies a year worldwide are born preterm. And of those 15 million, 1 million of them will die, okay? You know, the closer you're born to 37 weeks, the healthier you're going to be. But that's provided that you're born in a place that has a tertiary care centre like the NICU at UH. So really, we want to understand, why does labour happen early, and can we stop it? There's also post-term birth. 5% of babies go post-term, or pregnancies go post-term, but that's not such a big problem nowadays because these pregnancies are usually delivered by C-section. But if there wasn't an obstetrics department nearby, these women would have a really hard time surviving the pregnancy because the baby gets too big, and there'd be a disproportion between the cervical opening and delivering that large baby. Okay, so what are we trying to do? We're trying to understand how this one hormone called progesterone, which is a steroid hormone, to me, Not being a chemist, I always think of this as 2-deoxy chicken wire, but this is progesterone and it does remarkable things. It's called progesterone because it's progestational. It's the hormone of pregnancy. You need progesterone to get pregnant, you need progesterone to stay pregnant, and when it stops acting, pregnancy ends. And that's really the 90% of what we know about how progesterone works. But what we do know is that progesterone enters the cell, it interacts with these special receptors called progesterone receptors, as Dr. Liu alluded to. And this interaction of the progesterone with the progesterone receptors in those muscle cells of the uterus keep the uterus quiet. They block the progression of the uterus from the relaxed state to the laboring state. Okay, so this block is a mystery, and we're trying to understand how this block happens. The other thing we know is that the transition from the quiescent state to the laboring state is an inflammatory process. So that involves inflammation. We've all heard about inflammation. It causes pain and it's not good. But in this case, it's actually a physiological process that isn't involved with anything bad. It just causes this event to occur. So inflammation at the maternal fetal interface, where the maternal tissues touch the fetal tissues, causes the uterus to contract and the cervix to dilate and labor to occur. So what we've found through the experiments that I won't go into, but we developed model systems to look at the function of these progesterone receptors in individual cells and in tissues on a dish. And the bottom line is that progesterone blocks this inflammatory drive. So it acts as an anti-inflammatory only at these key cells in the uterus, because they're the only cells that have the progesterone receptor. And so what we know is that if this progesterone receptor signaling is interrupted, then it causes labor. So how does labor happen then? And to sort of skip forward probably about 5 to 10 years worth of work, this little connection here is what we've discovered in the last probably 5 years, that the inflammatory drivers, the exposure of the myometrium or the muscle of the uterus and the tissues of the uterus to factors that cause inflammation can actually prevent the progesterone receptors from mediating this stay pregnant, this block to labor. And so when we were getting our head around this, we thought, well, hold on, how could that be if this is having an anti-inflammatory effect, but the inflammation is blocking the progesterone receptor? How does a woman stay pregnant? Because any little bit of inflammation will inhibit the activity of the progesterone receptor complex within the cells. And then an aha moment was that, hold on, well, this may be threshold limited. So what I mean by that is this concept that through pregnancy, if you look at the x-axis here, which is time of gestation, so how long into the pregnancy are you, as pregnancy advances, the baby is maturing, the uterus is being distended, so there's fetal development, there's uterine distension. Some people argue that there's a placental clock ticking, and that all these factors add up to what we call an inflammatory load that's impacting the pregnant uterus. Okay, and that when this inflammatory load reaches a threshold value, then it triggers a signaling event within the cells of the uterus that kills this ability of progesterone to keep this under control. Okay, and once this is lost, then the inflammation has free rein. It's a positive feedback loop, and that leads to labor and delivery and emptying of the uterine contents. So you can imagine that if there were external factors or internal factors that change the shape of this trajectory, then the normal, which usually occurs at about 40 weeks, is going to occur earlier. So the curve is shifted to the left and the threshold is reached earlier, and then this would cause preterm birth. And one of the things we know is that the majority of preterm births are associated with intrauterine infection, fetal stress, and there's aspects of maternal stress that we still don't understand, both biological and psychosocial. Everything's biological, I guess, but maternal stress is a big factor in determining the shape of this trajectory. And so from this concept, we're very interested in understanding various aspects of this. First of all, clinically, can we determine where a woman is through gestation on her journey towards this threshold? So perform personalized medicine on every individual patient and assess her risk for preterm birth based on her proximity to the threshold. That would at least tell us which patients we need to keep an eye on. We kind of know that already, but it's pretty rudimentary in many ways. And then secondly, can we understand the biochemistry and molecular biology of how this inflammatory signal affects progesterone receptor signaling within the cells? And the fundamental question of how progesterone through the PR, the progesterone receptor, is actually having an anti-inflammatory effects within the uterine cells. So this is where we're targeting our therapeutics, and this is where the collaboration with Greg Tochtrop and Fakko Vandeneyken, we've come up with some very interesting compounds that boost this activity and inhibit this activity. They're progestin-like compounds, so they'll bind the progesterone receptor. And one of these compounds, actually several of them now, we've been able to test in a preclinical model, which is a mouse model of preterm birth. So in the mouse, it has a gestation of usually 19 and a half days, and birth is usually preceded by a drop in the systemic or the progesterone levels. So this is what we call a systemic progesterone withdrawal. But what we can do in the mouse is give the mouse an inflammatory challenge, which is lipopolysaccharide, this LPS, which is the component in the wall of E. coli that causes you to get sick, that causes your immune system to say something's wrong here. So if we treat the mice with a little bit of LPS, they'll actually go into labor within 24 hours and empty their uterus. And so we think that this is the human system, in that we have inflammation-induced birth without the withdrawal of progesterone. And we think that this is the embedded in the mouse here is the model that's happening in women. So we figured, well, what if we take some of these selective progesterone receptor compounds and put them into mice and then challenge them with LPS and see what happens. So in the vehicle-controlled animals, and this is a typical experiment that we would do, if we have 10 animals and we treat them with LPS, 6 out of 10 of them will go into preterm labor and deliver at 15.5 days. But if we treat them with one of our sperm compounds that we've called APA1, then only 3 out of 10 of these animals will go into preterm birth in response to the LPS. So we've decreased the incidence of preterm birth by 50%. Now that's pretty significant. And of these animals that got treated, 7 out of 10 of them go on to have a normal pregnancy and deliver healthy pups. Whereas 6 out of the 10 here delivered, so the ones that were left, 4 out of the 10. So we've increased neonatal health and the success of pregnancy. So by understanding the molecular biology of progesterone receptor signaling, the biochemistry, the cell-cell interactions, and the protein-protein interactions that are happening within the cells, we're able to design compounds that will exploit this natural action of progesterone to be the hormone of pregnancy, the progestational hormone that blocks labor, and boost its labor blocking activity. And so the dream in the future is that we develop therapies that are prophylactic, that every woman will take these therapies just like they take prenatal vitamins in order to boost the capacity of their progesterone to keep the uterus quiescent and decrease her risk for a preterm birth. All right, so enough of the science. Let's talk about the journey. So I began, as Jim pointed out, as a PhD student in Melbourne, Australia at Monash University in the Department of Physiology. And that's where I first learnt about fetal development and the concept of the fetus and the mother interacting. Then after gaining my PhD, I did a postdoc in San Francisco Wonderful time in San Francisco. I worked in the laboratory of Robert Jaffe, who Jim didn't tell you, but Bob Jaffe and Sam Yen, who was Jim's mentor, wrote a textbook together, and which is the one of the Bibles for reproductive endocrinology and infertility. And so at the time that I was training under Bob Jaffe, Jim was also working, training under Sam Yen. And so we have that in common in our pedigree. And so it was a hoot when I learned that, because Jaffe and Yen were, and there was lots of stories I could tell there. In any event, I spent a wonderful 10 years in San Francisco as a postdoc and then as a junior faculty. Then the main thing that happened in San Francisco was that I met my wife, and that was life-changing. And so from San Francisco, we moved to Newcastle, and I was a junior, well, actually mid-level faculty there at the University of Newcastle at John Hunter Hospital, and that's where I started to focus in on the role of progesterone and steroid hormones in human pregnancy and preterm birth. And then from Newcastle, as I mentioned earlier, that chance meeting with Dinesh Shah at the Society of Reproductive Investigation meeting in 2002 set off a chain of events that led us to Cleveland and to Case Western Reserve University, and here we are. So I owe all this really to my wonderful and beautiful wife, Laura, who we met in the lab. She understands me, she gets me. When I say I need to go and deal with some cells and change media, she knows exactly what's going on when I have grant trauma. And so it's just, you need this safety net as a scientist, when you can be so entrenched in what you do, to have somebody who'll be a backup and bring you back down to earth, plus be a best friend and the mother of our kids, Luke and Sarah, who are just wonderful, and it's such a privilege to see them become the adults they've become, and I'm so proud. I have a US family, and this is a recent family shot of our one of the reunions we have in at Silver Bay in upstate New York. Bunch of buffoons, really, but we have a lot of fun, and there's a lot of love in there. And this is us at Sarah's graduation dinner recently. We all love Italian food, and we're sitting around at a wonderful restaurant in St. Louis eating Italian food. Laura's dad, his wife, and Laura's mom and her husband, and Luke and Sarah and Laura. Now, I also have an Australian family, and I was looking for images of the family, and that had everybody, my sisters, my 4 sisters and my brother and my mum and dad. And I couldn't find any on my laptop except for this one. And this is an image that was taken 60 odd years ago, 61 years ago and a bit. Well, actually, yeah, 60 years ago. And this is my christening. And so this is my brother Frank, my sister Rita in ascending age, Rita, Anna, Lena, and Teresa, my dad and my mom. I don't have any memory of this, obviously, of this image being taken, except I have a memory of everything downstream of this image. And every time I look at this image, it makes sense of my memories downstream. There's a lot of smiling faces. There are cousins. There are people from the same village as mum and dad emigrated from in the south of Italy. This is a first-generation Italian story in Melbourne, Australia, and everyone is having. There's hot and cold running kids, which is typical of an Italian family, and every time I look at this, I think, well, that makes absolute sense why I turned out the way I did. I love Italian food, and I love my family, and my family loved me, and so at the time, my brother Frank was in his 20s and starting his own life, but my formative years it was really, I had four different mothers, Rita, Anna, Lena, and Teresa. And that experience, and my mom, of course, that experience really shaped who I am. And my wife keeps telling me that you were spoiled rotten. Well, you can't choose your birth order, and you can't choose the fact that you were born as the baby of four sisters, older sisters. And so I benefited from that, and I constantly am appreciative of everything that I was able to experience as growing up in this environment, but also still with my sisters and my brother in the love we have for each other. Now, one thing I want to mention in this photo, we don't know who took the photo, but whoever did Rita was about to throttle that person. And this look in Rita's eyes, I think, is the scariest thing I've ever seen. And so I don't know what happened after the picture was taken, but she was not happy. The other thing you don't see here is that there's a big keg at one side, and that's probably why everybody's smiling so much. I'll end with this picture. This is a more recent picture, 60 years later, of my four sisters and me during a trip to Australia. We haven't changed a bit, and so that's all I have. I just want to say thank you to everybody for being collegiate or the academic side of my life and the family side of my life, and so I'll end it there and just thank you.
That was incredible. Dr. Messiano, I want to thank you and Dr. Chakrapani for sharing incredible journeys that both of you have had and reinforcing why we have these celebrations. Endowed professorships are for the two of you. That's what they were created for. It's the elite of our educators, scientists, doctors, scholars, and we're proud of everyone that we bestow. It's an incredible honor. And I hope you enjoy your positions for years and decades to come. As Drs. Boron, Lou, and I know, having an endowed professorship is indeed special. And so we appreciate you, and we hope you appreciate us being able to bestow this. Now, it turns out that this is the fun part. The actual chairs with engraved in your names were delivered to both of you, and so I am hopeful that you can now sit in them. Dr. Sudha Chakrapani as the Joseph T. Weir, MD Professor, University Professor of Medicine, and Dr. Sam Messiano as the Walter H. Weir, MD Professor of Reproductive Biology. So we'd love to show off your sitting in the chairs. If we can get a picture of that, that would be great. There we go. And I'd love to have you all celebrate wherever we are. If there's a glass to be toasted, that would be great. And we've provided dinner and enjoyment. So I hope you can relax and enjoy yourselves. I wish we were all together. Someday soon we will be when all of your work helps us lessen the impact of this and the next pandemic. So congratulations to Sudha and Sam. I appreciate everything you've done. Thank you, Drs. Boron and Lou, for your introduction. And I hope you all have a good evening with your families soon. Thank you. Cheers.
Cheers.
All right, I want to thank you all. We're going to end our celebratory session at in a turn, and I appreciate everybody attending, family and faculty and all. Okay, have a good evening. Bye-bye.